Hi, everyone, and welcome back. It's Kira Garfolo with Math 109 at Greenville Tech. Today, we're going to talk about section 5.3, which is exponential and logarithmic equations. Basically, we're going to put everything that we learned in the last two sections together to solve algebraic equations. Remember that logarithms are just inverses of exponential functions. We can use this idea to help us solve exponential equations. Remember, we saw in the last section how it's difficult without logarithms to get difficult or even impossible to get a variable down from that exponent. So we're going to use this inverse concept to help us solve these exponential equations. In general, if you have an exponential and you want to use logarithmic form, rearrange the equation to get the base raised to a power alone on one side, and then you're going to rewrite the entire function in logarithmic form. So basically, you're going to take the log of both sides. Let's look at some examples. Let's say that we want to solve for t, and we have 3,000 equals 150 times 10 to the 4t. We want to round our final answer to 3 decimal places. Well, the first thing that we want to do is get that 150 over on the other side so that we're left with only 10 to the 4t on one side. If we divide off that 150, we're going to get 20 equals 10 to the 4t. Now we need to take a log to write our equation on both sides. So we say, okay, well, log base 10 of 20 equals log base 10 of 10 to the 4t. As long as we do it to both sides, we'll be good. So remember that log base 10 is going to give us the common log anyway. We chose 10 here because it's 10 to the here. But remember that 10 to the 10 to the 4t, that's just going to mean this term right here is going to be 4t. So we're left with log 20 equals 4t to the log 10, because remember we're using the exponent rule here. Log 20 equals 4 times t, and t is going to equal log 20 over 4, which we can use our calculator at this point because we can use the common log in our calculator. So we get t is 0.325. So again, get this on its own, and then take one of the logs. Here we use log base 10 because there's a 10. It's just kind of the more natural way to go. But we're going to see some other examples where we can take other steps. If you wanted to do this graphically, say that I didn't ask you to solve it algebraically, or you were just having to solve it on your own, or you wanted to check your work, you can go back to the methods we've learned already. Earlier in chapter 2, we used the intersect feature in our calculator. So you would want to graph 3,000, y equals 3,000, and also y equals 150 times 10 to the 4t. Just be sure that you enter it carefully over here, okay? Remember, t is going to be x in your calculator. It just holds that place with any variable. You'll graph them, and then you'll use that calc intersect to find the x value where they intersect. So here, sure enough, like we found earlier, we get x equals 0.325, rounded to 3 decimal places. Definitely take a minute and make sure you can solve this, because that is going to be easier than using logs in many cases if you already have your calculator. It's a great way to check your work. Now let's look at another example. So suppose a fossil originally had 12 grams of radiocarbon, and now it only has 0.2 grams. We want to know how old the fossil is, given that the half-life of radiocarbon is 5730. Well, to do this, we have to remember the half-life formula. So remember here that P naught is the original amount, P of t is what is left after t years, and K is the half-life. So our formula is P of t, so what's left after t years equals the original amount, P naught, times 1/2 raised to t over K. So for our situation, we have 0.2 because that's what's left, equals 12 because that's what we started with, times 1/2 to the t over 5730. Okay, so we can do some math here. We can get rid of this 12. We can pull it over there. So we get 0.2 equals 0.5 to the t over 5730. And then we get log of 0.5 of each side, right? And so we can solve for t using some basic algebra. However, we're going to run into a problem here. You can't just type this into your calculator. Remember, log of 0.5 with log of a base of 0.5 can't be input into a calculator. Our calculators can only do the common log, which is log base 10 of a number, and it can do the natural log, which is log base e of a number. So what do? We can apply what is called the change of base formula. The change of base formula allows us to use any base we want. We can choose our base from an original statement. So if we have log base a of x, then that is going to be equivalent to log base b of x over log base b of a. So log any base of x over log any base of a. The cool thing here is you can choose your base b. That means we can choose the bases the calculator works with. So as long as our base is greater than 0 and not equal to 1, we can use log base e to give us a natural log, or we can use log base 10 to give us the common log, both of which are available in the calculator. So this right here is the take-home message from this slide. If you have log base a of x, you can then transform that into log of x over log of a, or you can transform it into natural log of x over natural log of a. These are equivalent to each other, okay, all three of these. You do not need to put it into both of these, just pick which one is your favorite and go from there. They're going to give you the same answer in the calculator. So let's look at some examples for change of base. The first one, we have log base 3 of 17. So we know we can't enter that in our calculator, but we could use the common log of log 17 over log 3, or we could use the natural log of 17 over natural log of 3. I chose I'm showing you both, but I typically choose the natural log because, again, I'm a statistician, so we see natural logs a lot more in stats than we see common logs. So it's just kind of my instinct. But try this for yourself. Put both of these in the calculator, and you'll see that you get the exact same answer. So really, it's a personal preference. Now pause the video and give yourself a second, and I want you to use the change of base formula using either common logs or natural logs, or you can do both if you want to verify, to find log base 6 of 2 using your calculator with that change of base formula. When you're ready, you can see that log base 6 of 2 is going to be equal to the natural log of 2 over the natural log of 6, or the common log of 2 over the common log of 6. Again, they'll both give you the same answer of 0.387. So now we can continue our earlier example. We were left with t equals 5730 log of 0.5 of 0.2 over 12. Now this is still going to be a kind of ugly one, because applying the change of base, we can use the log or the natural log. The 5730 stays out the front, but now we're going to have log, natural log, if you want to use natural log, of 0.2 over the natural log of 12. So putting that in there, we get 5730 times these natural logs, which is going to give us somewhere around 33,846 years. So make sure that you can go back here. You can solve this piece to get to this piece, okay? So remember that we chose 0.5 here because it was one, excuse me, you're talking about 1/2. Okay, and then we use the change of base formula to get from here. Lots of careful parentheses in your calculator. Now we can also solve exponentials using log properties. Most of the time, this is my preferred approach. In fact, in our earlier example, I probably would have skipped straight to this if it weren't demonstrating that other approach. So what you're going to do is rearrange the equation to have a base raised to a power on one side. So just like before, you want that base raised to a power all alone on one side. Then you're going to take either the common log or the natural log, you can choose, of both sides. Remember, they're going to give you the same answer, so just pick one. What button do you like on your calculator better is really what it's going to come down to. Then you're going to use one of the logarithmic properties to remove the variable from the exponent, and you're going to solve for that variable. Let's look at some examples. Let's say that we want to solve for x in 3 to the 3x equals 19,683. We need to get that x, that 3x, down. We already have the base raised to a power only on one side. Let's take the natural log of both sides. Again, I typically choose natural log. All we did here is put natural log in front of each. So now we have natural log of 3 to the 3x equals natural log of 19,683. Notice here that we have an exponent, so we can use that power property and bring that down in front of the logarithm. So now we know that 3x times ln of 3 equals ln of 19,683. Now it's just basic algebra. We need that x by itself, so we need to divide off 3 and ln of 3 to get our final answer. So x is going to be that natural log over 3 times the natural log of 3, which if we plug that into our calculator, we'll see that it equals a perfect value of 3. Pause for a moment, make sure that you can solve this, go back, make sense of it. Again, when you see that x there, get it all on its own on one side, take the natural log or common log of both sides, it'll give you the same answer, and solve for x. Now you try it. Pause this, give yourself a minute, and then we'll walk through the solution. Okay, so first in this one, we need to get that number raised to the power on its own. We need to get rid of that 5. We'll divide the 5 off on both sides to get 0.3 to the 3x plus 7 equals 6. Now we're going to take either the common log or the natural log of both sides. Taking the natural log of both sides, this is what we get. We want to pull that 3x plus 7 down according to the power property. So we're going to be left with 3x plus 7 times ln of 0.3 equals ln of 6. And now it's just going to be some basic algebra. 3x plus 7 is going to be that ln of 6 over ln of 0.3. And now we just need to subtract that 7 and divide by 3. If we do all of that very carefully, plug it into our calculator, we get negative 2.83. If you made a mistake, go back and find it. It may not even be in your logs, it may be in the algebra at this point. If you're one of those people who doesn't like to leave all these natural logs, you could totally solve this piece here and just have one single decimal number so that you didn't have to look at this ugliness here. That is fine, but be careful. Make sure you carry a few extra decimal places so that you don't get rounding error that accumulates and ultimately gives you a wrong answer. It's one thing to be a little bit off on a test that I'm grading, but it's another thing to be a little bit off on homework that only allows so much room for error. It's going to mark it wrong and you're going to get frustrated. Now, we can work the other way too. Instead of solving exponentials, we can solve log equations. And guess what? We're going to still use the whole concept of the inverses to do that. We're going to work backwards, rearranging the equation to convert it to exponential form so that we can get rid of the logs. This doesn't always work out perfectly, but it's always worth a try. So for example, let's solve 6 plus 3 natural log of x equals 12. So again, we want to get rid of that 6 so that we only have the natural log over on one side. Get rid of that 3. So we end up with ln of x equals 2. And now what do we need to do? Well, remember that natural log is base e. So if we raise everything e to the everything power, which is the same as saying log base e, we can solve this. So e squared is going to give us x. And when we plug that in, remember e is a number. So whatever we use on our calculator, e squared is going to be 7.389 roughly. Okay. So remember that ln of x is the same as log base e of x. We know it equals 2, so e squared is going to give us x. Just like before, we can actually check this in our calculator also. Put left side in one y, right side in another y. You don't even have to simplify these. You can just put them in as they are. Minimizes your chances for a mistake too. And then use that intersect, that calc intersect once they're both graphed. On these, you may have to adjust your window, so remember that. But once you're there, you can use the intersect. And sure enough, we see 7.389 as our answer. Now, I like to use the log properties, if possible, to solve anything backwards this way. So we can often combine this step with converting to an exponential. So we kind of pair things together, everything that we've learned today, to get our final answer the simplest way. Let's look at an example. Let's solve ln of x plus 3 equals the ln of x plus 4. So first, let's get everything on one side with the ln's, okay? Everything that has a natural log on one side, everything that doesn't on the other side. So we're left with 3 equals the ln of x plus 4 minus the ln of x. Now remember, this can't be broken down any further. It has to be a product in there to make it work together. But we do see a natural log and a natural log, and they're separated by a subtraction. So we know that can actually be simplified to the natural log of x plus 4 over x, because it's the quotient property. Now, anytime we see an ln, we want to think e is base of e. So since it's a base of e, we're going to raise both sides e to that power. So we're going to say e to the 3, e to the ln of x plus 4. E to the ln of anything cancels out. So we're just left with e to the 3 equals x plus 4 over x. Now we're going to use some basic algebra. We don't have logarithms anymore, or really powers anymore. We're just going to have to solve for x. We pull that x off the bottom, pull the x to the side so we have all the x terms on the left, factor out the x, divide off what's left, and we get x equals 0.21. See if you can try this for yourself. Again, if you use natural log here, raising e to the ln of something is going to just leave you this. It's that kind of cancel out on the property from the last section that we talked about, because remember, this is log base e. So we're taking e raised to the log base e of something, and they cancel out. So that's all that we have. You'll need lots and lots of practice to put these puzzles together. So most of this section is just applying and getting more practice with what we've already learned in the previous sections. Remember that the change of base rule is helpful. You can use ln or you can use common log. Use whichever one you prefer. Again, I usually use natural log if you're looking at my materials, just because it's more natural to me. I've used it for a lot longer. But common log will give you the exact same answer, so if you prefer that, go for it. Remember that e to the natural log of x is going to give you x, because that's e to the log base e of x. So all that's left is x. And the natural log of e is 1, because log base e of e is going to be 1. These are very helpful if you're simplifying using the natural log. Logarithms take practice. Lots of practice, actually. So if in these first 3 sections you're a little bit frustrated, that's okay. Practice your homework. Practice extra problems in your text. Get some help if you need it. Remember, we're available. Also, remember that sometimes there are multiple ways to get the correct answer. As long as they're mathematically sound, that's fine. Just like using natural log versus the common log, just like applying certain things first. As long as you're following the order of operations and you're taking the right approach, maybe you want to exponentiate everything versus maybe I would take advantage of some properties to simplify first. We may both end up at the exact same answer, both mathematically correct, and that is fine. You use your preferred approach, just make sure you're comfortable with the rules and understand what's going on. Again, if you need further help, you know how to reach me. You can stop by my office hours, send me an email. Otherwise, you can also check out the Math Center. The tutors are available anytime at your convenience by scheduling. They also offer virtual sessions right now. So keep practicing, don't get frustrated, and I hope to see you next time.